Okay, variations in atomic structure implies we're talking about variations in the nuclear structure and variations in the electronic structure. When we talk about variations in the nuclear structure, we're talking about isotopes. The term is isotopes. An isotope, or isotopes, represents a set of elements having the same atomic number. But different atomic masses. And this is primarily due to variations in numbers of neutrons. Now, one set of isotopes that is very important, I want you to learn the names of this. I don't ask you to learn names of them, but that's the hydrogen set. Hydrogen isotopes are called protium, deuterium, and tritium. And one symbology that's used is to illustrate only the symbol and the mass weight rounded to the nearest whole number. And this is referred to as hydrogen 1, hydrogen 2, and hydrogen 3, heavy hydrogens, if you will. Now, this one, of course, all of them have the same number of protons, 1, 1, and 1. But the number of neutrons is where the variations occur relative to that mass number. Protium does not have neutrons. There's only one proton and one electron making up its atomic structure. But deuterium has a neutron and a proton, and tritium has 2 neutrons and a proton. And just as a trivia note, you'll learn more about this when you get deep into Chem 2, is that interaction of deuterium and tritium is the fundamental energy source for the sun and stars. Here is just for your interest, 1 plus hydrogen 2 and 1. That's wrong. 2 and 1 and 3 and 1. Sorry, because atomic mass is the sum of. Okay, this will go to what we call helium, 4 and 2 plus a neutron, and let's see, I have hydrogen 1. Should have a neutron, 1, 2, 3, 1, 2. No, it's not balancing out. And that's gamma ray out there on the end. Oh, that's 5, 4. I see what my problem is. There we go. There we go. Getting the notations right. 4 and 1, 3 and 2 is 5, and then this is a gamma ray. No, this is just high energy. But this is the energy of the sun. just as a trivia note, and that hydrogen interacts with hydrogen, and it's called nuclear fusion. No, I'm not asking you to repeat that on test day. You're not worried about it. And deep into Chem 2, you will. But I thought it's kind of an interesting footnote about isotopes, especially those of hydrogen. Yes, you are responsible for the names of the 3 isotopes. But at any rate, from here, we can use the mass numbers of isotopes to define what we call the weight average atomic mass. The weight average atomic mass is the number that's on the periodic chart. Okay? Looking at your handout, you'll see some bunch of numbers, but there are 3 isotopes there are actually more than that, but these are the 3 primary isotopes of oxygen that contribute to determining the weight average atomic weight, which is the number on the periodic chart. Well, how do you get to that? Well, the number over here, called the fractional abundance, represents the, actually converted to percentage. This is the most abundant form of oxygen, oxygen 16. Okay? 99.7620%. And then there's oxygen 17, well, it's only 0.0373%. And of course 18 is 0.2014%. So the oxygen 16 represents the significantly greater contribution as far as structure goes. Well, if we multiply fractional abundance times the isotopic mass, we get what we call the weight average contribution of each element. I get 15.9568. If somebody would back me up on that, I'd appreciate it. So what we did was we just simply multiplied the isotopic mass given times its fractional abundance. Sometimes they give the fractional abundance on problems in percentages. So if you're trying to calculate a weighted average, be sure to convert your percentage to a decimal fraction. Okay? And you multiply them together, same way with the 017, 018. Write those down, please. Now, to get the total weight average contribution, we simply add these individual weight average contributions to get the total. And when you do, you get 15.9994. Now, it is different than this first one, 9949. If you look on the periodic table, the weighted average is 9994. And so all of the elements have a set of isotopes and, of course, associated fractional abundance. And so some guy in a basement of a big building somewhere figures out all these little weighted average contributions, adds them up, publishes a periodic chart. So that's where those numbers come from. The sum of the isotopic weighted averages, like that. Now, right now, the units that are associated with this are AMUs. And AMU is an atomic mass unit. An atomic mass unit is a relative mass weight. What do I mean by that? Well, it's relative to carbon-12 is what the reference number is. So there is a mass of oxygen over a mass of carbon. So we have carbon to oxygen ratio of 12.000 slash 15.9994, like that. And some people will go oxygen to carbon, but it indicates that relative mass means what? It means that that element is so many times heavier than carbon. So that's a 1 to 1.33328. So oxygen is 1.33328 times heavier than carbon. And if you go back to hydrogen, it'd be 1/12. So the hydrogen mass is 1/12 of that of carbon. So when we look at the organization of the mass numbers, they are there in terms of how much heavier or lighter they are relative to the standard carbon, or carbon-12 is what it's referred to. And only represents I'm heavier or lighter by so many times. That's all it means. Electronic structure. Of the atom, if you want to put it out there. Now, by the octet rule, electrons are gained or lost, depending on the element, at the valence level. So forth. Octet. So we can, the first thing we need to understand is that an element that gains or loses electrons goes to ions. And there are two kinds of ions. Ion is a charged particle. By definition. You have cations and anions. So cations have a positive charge and anions have a negative charge. Well, how do you tell the difference just from the terminology? Cation has a positive right in the middle of it. Okay, and the other one is a negative ion. It's just a memory thing. But in general, when we talk about the metals, we can generally say these tend to lose electrons and become cations. Nonmetals, and we include all of those elements to the right of that staircase in a general idea, and as non-metals in this discussion, and all the elements to the left of that staircase in the periodic table are your metals. And so the metals, non-metals, tend to gain, as we explained earlier. And these produce anions. Let's see, remember that. So when we look at the periodic table, we can also tell what the charge on an element will be as a result of gain or loss of electrons. Yeah, sorry. Anyway, these elements have one outer shell electron. Elements have two outer shell electrons, including the transition and inner transitions up to the staircase. Put that back in here. Tend to lose electrons. positive charges. Now, how much charge does that represent? Incidentally, to save us time, the charge on an element, or what we call polyions, structure with a charge, called oxidation states. So we're talking about oxidation states now. Oxidation states of elements by themselves. Now, if you put that element into a compound, you can have a variety of oxidation states. But right now, we're just talking about individual elements. And I will explain at the proper time how to distinguish between what is what. Group 1A has one outer shell electron. It's going to lose one electron. That means it's deficient by one electron, or one negative charge. Well, you can't change the proton number. If you do, you change the element. So in all of what I'm saying, the proton numbers are constant, but the electron numbers vary relative to the group they're in. All of the elements in group 1 lose one electron. This leaves an extra proton, that's positive charge. So everybody in this becomes +1. Anybody in this group loses that valence electron. What remains is the core structure. Core structures are inherently stable under normal chemical and physical experience or conditions. The core structures will not undergo change. In group 2, having two outer shell electrons, will tend to lose those outer shell electrons to achieve a noble gas configuration, leaving a surplus of 2 protons, or +2 for each one of these. And group 3, we'll go all the way down just for what we're doing here. Now, you put those in compounds, there is, some changes. But right now, individual elements follow this trend. Group 4 has 4 outer shell electrons. Well, that's the bridge, as we call it, from metals into nonmetals. So we start at group 4 gaining electrons to achieve a noble gas configuration. So when we gain 4 electrons here, that's going to have a surplus of 4 negatives above the number of positives. So this has a -4 all the way down. Nitrogen has 5 outer shell electrons, group 5. To achieve an octet, it must gain 3. So nitrogen, all the way down, for right now, will gain 3 and carry a -3 charge. Oxygen, 6. Sulfur, selenium, tellurium, on down, -2. Halogens have 7, need 1. They will carry a -1. And, of course, zeros for the noble gas configuration. So you can look at the periodic table and say, well, that's in column whatever. Now, in the transition collection and the intertransition collections, some are fixed charge oxidation states and some are variable charge oxidation states. There is a pattern in here that I want you to kind of follow to help you remember what these are. When we talk about fixed charge oxidation states, the elements I'm about to show you do not change regardless of where they go. Okay? The place you need to start here is silver, right here. Number 47. And we'll work with tantalum also. So if you can find those two, you can get the rest of the fixed charge, the rest of the fixed charge elements in here. Come to the right by 1 step and block in zinc and cadmium. Like this. So you got 1 block here for silver, 2 blocks for zinc and cadmium, and then I'll show you aluminum, gallium, indium over here plus 3. On the left over here, you got 1 block, and then go step left, 2 blocks. And this is circumstantial. This is not scientific, but it'll help you remember or locate who's who. Then step left again, 3 blocks, like that. The following rules apply. Group 1, Group 2A, and Group 7A are fixed charge groups. They don't change, regardless of, by themselves. And I'll explain later. There's a lot more to go. But we talk about fixed charge group 1. Alkali metals always have a +1 charge. Alkali earth metals always have a +2 charge. And halogens always have a -1 charge based on some other rules that I'm going to give you later. For right now, as far as you know, and until I say different, that's what they are. So those are fixed charge. There. Now, these are also fixed charge that are blocked off here. Now, on the right side, you have 1 block, 2 blocks, and 3 blocks that I've squared out here. Silver is always a +1. 2 blocks. Zinc and cadmium are always +2s. Aluminum, gallium, and indium are always +3. So 1 block, 2 blocks, 3 blocks. And circumstantial. It has nothing to do with the science of what we're talking about. But it helps you, it's a device, geometric pattern recognition device to help you remember those. Tantalum, hafnium, zirconium, selenium, uridium, and lanthanum. Okay. Now, this one, you have to count left to right. 1, 2, these 3 blocks, yeah, well, that's convenient. 3, but the zirconium and hafnium are +4s, fixed charge, and this is +5s on those transitions. Here's the rule. If they are not a member of what I've identified here, as far as listed, they are variable charges. So any of the transitions in here and inner transitions that I haven't blocked are variable charges. And probably next class, and it will be next class, we'll show you how to determine what the charge on a given element is based on its formula. And we'll learn to write formulas stuff next class. So this is your first objective. Now on your quiz, I'm going to give you a couple of quizzes next time. I'll give you a periodic chart. I'll hand it out one of these generic periodic charts, and you can use that to answer the question. Always do that. So, but you still need to know the pattern recognition for the oxidation states, and it's important that you understand these at this point, because next class we'll be writing formulas and giving you the rules for that. Okay, here's where we are in our coverage. I've got some YouTube videos in here that I would encourage you to go look at. So if you go online, this is posted in the outline on Chem Unlimited. And so all of these topics have been covered. Okay? Additional reading is suggested in Chapter 2 of Ebbing, along with the noted videos. Any problems you can work at the end of the chapter to your advantage, answering questions. Just don't have time to do all those right now. So based on the material you have, this is where we are. Now, next class we'll start with how to write formulas and name and nomenclature and on like that.